I'm Anil Kumar. Welcome to my series on complex numbers. In review part 2, we'll look into these 5 questions. The idea is basically to understand how to show or represent complex numbers on a complex number plane and how to perform basic operations on complex numbers. Let's recall a complex number z is written as a plus bi, where this is the real part and this is the imaginary part. Now I square is equal to minus 1, or sometimes we write square root of minus 1 is equal to I or iota. When we talk about representing complex numbers on a plane, then it is similar to a Cartesian plane where one axis, the x-axis represents real numbers and the y-axis represents imaginary numbers. As far as the operations of complex numbers are concerned, they follow the same operations as we do with real numbers. That is to say, addition is commutative, we have associative property and the distributive property. So all these 3 properties are there for addition and also basically for addition, right? Also, one more thing, let's remind me, we should talk about is the conjugate. Conjugate is written as with a bar on the type and a minus bi will be conjugate of z, right? So we change the sign to make it a conjugate. So this conjugate helps to rationalize or to simplify complex numbers in a large way, which we are going to see in this particular video. So let's begin with the solution of question number 1 and see how it goes. Now let us see how to represent complex numbers on a complex number plane. So I was explaining the x-axis equivalent to our coordinate plane represents the real numbers and the y-axis represents the complex part, imaginary part, right? Now we have a number, the complex number given to us is 3 plus 2i. So let's call this 3 plus 2i as our complex number x. 3 is the real part, 2 is the imaginary part, positive 2. Right? So we'll take 3 units along the x-axis, 1, 2, 3, that's the real axis, 1, 2, 3, and then 2 units along the imaginary up, right? So that becomes the complex number, 3 plus 2i. Now, as you can see here, the representation is very similar to vectors. So this reminds me of vectors. In fact, most of the operations which we do with complex numbers, especially addition and subtraction, could be done exactly as we did for vectors. Now let's take up the next one, which is 2 minus 4i. Let's call this complex number as y, 2 minus 4i. So here again, 2 is the real part, so we'll go 2 units to the right. Well, I went 4 units here. Okay, so this was actually not 3 plus, this was actually, when I plotted, this becomes 4, right? So I went 1, 2, 3, 4 units and then 2 up. Okay, now let's go 2 minus 3i, 2 minus 4i. So 1, 2 and minus 4 means 1, 2, 3, 4. So that becomes 2 minus 4i. So this is 2 minus 4i, right? So you go 2 units to the right and 4 down. The last one here is minus 4 plus 3i. So 1, 2, 3, 4, that is minus 4. 1, 2, 3. And when you join with the origin, it gives you the complex number minus 4, let's call this as z, equals to minus 4 plus 3i. Okay? So that is how you could represent the complex numbers on a complex number plane. So I hope that is clear. To practice, you can take up another example. Let's say you have a complex number p, which we can take as minus 5 minus 6i, right? So it'll be in quadrant 3, correct? Okay, so let's move on and take up question number 2. Now we need to add 5 plus 2i and 1 minus 4i. And we also need to show that addition is commutative on a complex number plane. So we'll begin with 5 plus 2i. 1, 2, 3, 4, 5. 1, 2. So that is representation of complex number 5 plus 2i. Now if you want to add to this 1 minus 4i, then what you can do here is, from the tip of this complex number, which we call the head, we can begin the other complex number, which is 1 minus 4i. So 1 is the real part, so move 1 unit towards the right, and minus 4 imaginary part go 4 down. So you get 1, 2, 3, 4. So you basically reach this particular place. So that becomes the sum of these two complex numbers. And this sum can be represented by the vector with origin as the tail and head at this point, right? So this becomes the sum, which you will see will be 5 plus 1 as 6 and 2 minus 4 as minus 2i, right? So you can check 1, 2, 3, 4, 5, 6 and 2 units down. Do you see that part? So that is how we could actually add the complex numbers on a complex number plane. Now, as I was saying, these complex numbers, in these complex numbers, addition is commutative. That is to say, we could have started with 1 minus 4i, correct? So let's do that part. 1 minus 4i, if I do 1 and then 4, 1, 2, 3, 4. The complex number will be 1 minus 4i written as this. Now here, we are going to now add 5 plus 2i. So starting from the head, we can go 5 units to the right, 1, 2, 3, 4, 5, and 2 up, 1, 2. So you see you reach the same spot, right? So if you do this, what do you get? The addition is again the same. 5 plus 1 is 6, minus 4 plus 2 is minus 2i. So you have the same result. So you can see here that addition is commutative. By taking 3 vectors, you could also show that addition is associative. So let this be an exercise. So that is to show that, let's say you take 3 plus 2i plus 1 minus 4i plus 4 plus 2i. Okay? So show that addition is commutative using these vectors. Associative. Okay, let's move on and take question number 3. Now let us see how to find square of a complex number. So when I say square, basically it means you multiply the number by itself, right? So that becomes the square. Right? So square, let's say this is a complex number z. So you could write this as 3 minus 4i times 3 minus 4i. You could also use the formula a plus b or a minus b whole square. Let me write here. So a plus or minus b whole square could be written as a squared plus or minus 2ab plus b squared. And remember, I square is equal to minus 1, correct? So I'm going the long way. Square means multiply these two binomials, right, with the complex and real parts. So 3 times 3 will give us 9. So first you have to multiply with 3. So 3 times 3. And then minus 3 times 4i. With minus 4i, you can write minus 4i times 3. And then minus minus becomes plus. So we'll write 4i times 4i, correct? So that gives you 9 minus 12i. This is also minus 12i. And that makes it 16i squared. Now I squared is negative, right? So we get 9 minus, we can combine these two, 24i. And here we get minus 16 since I squared is negative 1. Perfect. So combining these two, minus 16 and plus 9, what do you get? You get negative 7 minus 24i. So that is how we can actually combine these terms and write down the solution, correct? You could have done direct also. So if you do direct, you will get 3 squared minus 2ab, that is 2 times 3 times 4i plus 4i square, right? Whole square. So that gives you 3 square is 9 minus 4 times 6, 24i, and that gives you minus 16i. So you get the same result, correct? So that is how you can actually do directly or as we did. Perfect. Let's move on and take question number 4. Simplify reciprocal of 4 minus 3i and write as a plus bi. Now we want to write this as a plus bi. Let me write a plus bi first. When we say reciprocal of means 1 over 4 minus 3i. Now we don't want the imaginary part to be in the denominator. So we actually perform operations similar to rationalization. We'll multiply and divide by its conjugate. Conjugate is 4 plus 3i for the given complex number. So we have 1 over 4 minus 3i times 4 plus 3i over 4 plus 3i. So in the numerator, we have 4 plus 3i now. However, in the denominator, we have a plus b times a minus b, right? So when you do a plus b times a minus b, you get a squared minus b squared. So that is to say, we get 4 squared minus 3i whole square. And now you remember, I squared is minus 1. So that makes this positive, correct? So what we get here is 4 plus 3i over 16 plus 9, correct? So what you notice here is that the denominator becomes a real part. In this case, it is 25, right? So we could write this as 4 plus 3i over 25, or write it as 4 over 25 as the real part and 3 over 25 as the imaginary part, right? So that is in the form of a plus bi. So in complex numbers, you could expect a and b. These are actually the real numbers. You could write them as fractions as shown here. I hope that makes sense, right? Now the last question here is to write an equivalent expression for the cube. So we have 2 plus 3i whole cube. So I'll use the formula here. The formula is let's write down the formula. First, if I have a plus b whole cube, then it is equal to a cube plus 3 a square b plus 3 ab square plus b cube. Correct? So we'll directly apply this formula and expand. We'll try to understand what is I cube with this example. So what we get here is 2 cube plus 3 times 2 square times 3i plus 3 times 2 times 3i square plus 3i cube. Now 2 cube is 8. Now here we get 4 times 9 as 36i, and then we have here 9, 3 times 2 6, 6 times 9 54 I square, right, plus 3 cube is 27 I cube. Now what we know is I square is minus 1, right? So what we know here is that I square is minus 1. So I cube will be equal to minus 1 times I. So it is negative I, correct? So that is I cube. Okay. So what we get here is this I square is minus 1. So we can write this as 8 plus 36i minus 54. And here it is minus I. So we could write this as minus 27i. Correct? So that is how you could actually expand it. And now we can combine the terms. So let's do 8 minus 54, which is equal to minus 46. And the I terms is 36 minus 27, which gives us 9. So that is 2 plus 3i whole cube. So that is how you get your result. So 2 plus 3i whole cube is equal to now in your test you could get these questions as multiple choice questions. So I'd like you to understand few basic concepts about complex numbers as we have discussed in this review. Also go through review part 1 where we have taken up few more operations on complex numbers. In part 3 we'll have a multiple choice test on complex number which will prepare you for university admissions and for your own understanding of complex numbers. I hope that helps. Feel free to write your comments and share your views, and if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.